everyone, and welcome to part 3 of our Introduction to Risk Assessment. This is GCU from the University of Minnesota, and today we will focus on step 2 of the risk assessment process, dose response assessment. This step focuses on evaluating the relationship between the amount of a chemical someone is exposed to, which we call the dose, and the magnitude of the resulting health effect, which is the response. So, in simple terms, it answers the question, how much of this substance causes harm, and at what level does it become dangerous? The purpose of this step is to determine a health benchmark for exposure to the hazard. This benchmark is usually expressed as the amount of contaminant in milligrams per kilogram of body weight per day. Dose response data is gathered from toxicological or epidemiological studies, and it's used to establish what might be considered a safe limit of that contaminant in the human body. Sources of information for this step typically include the EPA's Integrated Risk Information System, or IRIS, and the Agency for Toxic Substances and Disease Registry, known as ATSDR. These organizations provide toxicological profiles and dose response data for a wide range of substances. This step lays the foundation for understanding how increases in the amount of a toxin in the body results in increased adverse health effects. When we talk about dose response, the first step is to understand what we mean by response. In toxicology, response is the body's reaction to a dose of a substance. If we look at the graph, dose is on the x-axis and response on the y-axis. These curves show that the relationship can take different forms. A linear relationship means the response increases steadily with dose, while a nonlinear relationship shows that the response may start more gradually and then change more sharply as the dose increases. The important idea here is that response dose not always look the same. It can vary depending on the chemical and the biological process involved. Now, let's take a closer look at the types of effects we consider in a dose response assessment. There are two main categories, threshold effects and non-threshold effects. Threshold effects refer to situations where a certain level of exposure or dose must be reached before any adverse health effects occur. These are typically non-carcinogenic effects, such as liver damage. For these types of effects, we assume there is a safe level or exposure below which no harm is expected. The benchmarks used here include RFD, reference dose, TDI, tolerable daily intake, and ADI, acceptable daily intake. On the other hand, non-threshold effects are typically associated with carcinogenic outcomes, like cancer. For these, we assume no level of exposure is completely safe, meaning even the smallest dose could carry some risk. So instead of using a safe threshold, we use values like slope factor or unit risk to estimate the probability of developing cancer from a given exposure. On this slide, we're introducing an important concept in dose response assessment, the reference dose, or RFD. RFD, which is developed by EPA, and it is an estimate of the daily oral or dermal exposure to a chemical that is likely to be without a significant risk of harmful effects over a person's lifetime. This estimate includes a safety buffer and considers sensitive subgroups such as children or the elderly. It's important to note that this is not an exact threshold. There is some uncertainty often by a factor of 10 or more, built into the estimate to account for variability in human response. The unit for RFD is typically expressed as milligrams of contaminant per kilogram of body weight per day, or simply milligram per kilogram per day. RFD is used as a benchmark to help determine whether a certain level of chemical exposure is likely to be safe or not. This slide introduces another key term used in dose response assessment, the reference concentration or RFC. RFC is similar in concept to the RFD we just discussed, but it applies to inhalation exposure rather than oral or dermal routes. It's defined as an estimate of a continuous inhalation exposure to the human population, again, including sensitive subgroups, that is likely to be without an appreciable risk of harmful health effects over a lifetime. As with RFD, there's inherent uncertainty, often spanning an order of magnitude. These units used for RFC are typically milligrams per liter or parts per million. This value helps us determine what concentration of a chemical in the air is considered safe for long-term exposure. Now let's talk about another important term, the minimal risk level, or MRL, which comes from ATSDR, the Agency for Toxic Substances and Disease Registry. The MRL is an estimate of the daily human exposure to hazardous substance that is not expected to cause adverse non-cancer health effects, even when exposure happens over a specified time period. You can think of it as essentially a safe level of exposure. Importantly, the MRL is conceptually the same as the reference dose, or RFD, used by EPA. Both represent the maximum daily exposure without appreciable risk. The main difference lies in the agency that develops the value. Often, these values are the same, but they can differ if the agencies rely on different toxicology studies to derive the number. Let's go over an important concept in dose response assessment, the point of departure, or POD. On the left, you can see a typical dose response curve. The POD is marked near the bottom of the curve. This is the point at which we start to see a measurable biological response to a chemical. It's usually based on experimental or observational data and reflects the lowest observed effect level, or sometimes a no observed effect level. The POD serves as the starting point for calculating reference values like the RFD or MLL by applying uncertainty factors to ensure safety. So in short, the POD is where we begin the process of setting health-based exposure limits. Now let's look at one of the most commonly used point of departure, the NOAEL, or no observed adverse effect level. This is defined as the highest dose at which no harmful or toxic effects are observed in the study. In other words, it's the threshold level where we're still not seeing any adverse health outcomes in the test population. You can see this illustrated in the dose response curve on the right. The NOAEL is the point just before the curve starts to rise, meaning no effects have been observed yet. Once we go beyond that, we reach the LOAEL, or lowest observed effect level, where effects begin to appear. NOAEL is often used in risk assessment to help determine safe exposure levels. Another commonly used point of departure is LOAEL, which stands for lowest observed adverse effect level. This is defined as the lowest dose at which we begin to see an observed toxic or adverse effect in the study population. In the dose-response plot, the low IL is the first point where the response clearly rises above the baseline, indicating the onset of a harmful effect. It's important because it helps identify the point where risk begins and is often used in risk assessments when a NOAEL is not available. By understanding both NOAEL and low-IL, we can better evaluate the relationship between exposure levels and health outcomes. Now that we've introduced the concept of NOAEL, let's talk about how it's used to determine MRL or minimal risk level. A NOAEL is typically determined from toxicological studies, most often conducted using animal subjects. It is expressed in units of milligrams of the substance per kilogram of body weight per day. But since animal data isn't a perfect reflection of human response, we apply what are called uncertainty factors or UFs. These help us account for potential differences between animals and humans and for sensitive subgroups in the human population like infants or the elderly. For example, we might apply a factor of 3 for extrapolation from animals to humans and another factor of 10 for population sensitivity. So the MLL is calculated by dividing the NOAEL by the total uncertainty factors, as shown in the equation MRL equal NOAEL divided by UFs. This gives us a conservative estimate of a level of human exposure that's likely to be safe. Let's now look at a key term related to cancer risk assessment, the slope factor or SF. This graph shows a dose-response curve for a carcinogenic substance. The x-axis represents dose and the y-axis represents the probability of developing cancer, not a guaranteed outcome. These curves are based on test results, usually from high-dose animal tests. To estimate risk at lower doses, scientists use a method called linear extrapolation, drawing a straight line from the lowest observed cancer-causing dose down to 0. The slope of this line, often labeled as A over B, represents the slope factor. It gives us a way to estimate the increased probability of cancer per unit of exposure to a carcinogen. In other words, it tells us the added risk of developing cancer as the outcome of the risk assessment rather than predicting a certain number of cases. Cancer slope factor equals incremental cancer risk divided by average daily dose. This value helps us estimate how much cancer risk increases with each additional unit of exposure over a lifetime. In this slide, we will briefly go over different risk assessment approaches and how they are applied. First, we have the non-cancer risk approach. This method is used to estimate a safe level of exposure, often referred to as the reference dose or reference concentration from EPA, and minimal risk level or MLL from ATSDR. These values are derived from NOAEL or low-IL using uncertainty factors to account for sensitive populations or gaps in the data. Next is a cancer risk approach. Unlike the non-cancer approach, this one assumes there is no safe level of exposure. Instead of identifying a threshold, we use a slope factor to estimate the risk of cancer. The formula is shown here as risk equals LADD, the lifetime average daily dose, multiplied by the slope factor. Then we have benchmark dose modeling, or BMD. This is a more advanced statistical method that's often used in place or NOAEL or low-IL. It uses the full dose response dataset and tends to provide a more accurate and robust point of departure. And finally, all of these methods lead to the outcome. Establishing safe exposure limits. These limits are used by regulatory agencies like the EPA and WHO to guide risk management decisions and protect public health.
This lesson has been created by the Interdisciplinary Training, Education, and Research Activities for Assessing and Controlling Contaminants from Emerging Technologies Program, a collaboration of the University of Minnesota School of Public Health, the University of Iowa College of Public Health, and the University of California, Los Angeles Fielding School of Public Health. Funding for InTERACCT is provided by the National Institute of Environmental Health Sciences of the National Institutes of Health. The content of this lesson is the sole responsibility of the developers and does not necessarily represent the official views of the National Institutes of Health.